The new section is entitled Estimating a Population Mean where sigma is known. The next section will be estimating a population mean where sigma, the standard deviation, is unknown. So sigma is known. And you want to estimate the population mean. There is basically two criteria to use the techniques of this section. The first one is the value of the population standard deviation, namely sigma, is known. And the second one is n is bigger than 30. Requirement is n is bigger than 30, or the population we are dealing with is normally distributed. If it's normally distributed or the sample size is bigger than 30, you can use the techniques of this section. The main thing we're going to be dealing with in this section is finding a confidence interval estimate of the population mean. And that requires us to know the formula for the margin of error, which is denoted by the letter Z. Excuse me, the letter E. I'm thinking of the next letter I'm going to write. E is equal to Z sub alpha over 2, the Z score associated with alpha over 2, times the standard deviation, which is known, divided by n, the sample size. And the confident interval has this formula. The confident interval estimate of the population mean, because we want to use the sample to estimate the true mean, the mean of the whole entire population that we're talking about, whether it be the weights of quarters, the weights of newborns, the average score of statistics students, or the average grades of statistics students, etc. The average salary of college graduates. We want to estimate the population mean, the mean average of all college graduates in the United States. So we're going to survey each and every college graduate in the U.S. and compute their average salary? No. We're going to take a sample. And we can use the techniques of this section if n is bigger than 30. Or is normally distributed. Okay, so now the confident interval estimate of the population mean mu, of course with sigma known, is nothing more than the average of the sample minus this error, which we calculate over here by that formula, and their sample mean plus the error. Now, the sample size, for estimating the mean mu is n is equal to Z sub alpha over 2 times sigma all over E. And whatever that is, you square it. So these are the two big formulas for this section. Calculating the sample size and how to calculate the confident interval estimate of the true mean. That is the population mean. Okay, so let's try a couple of problems. So again, we must make sure that it's normally distributed or n is bigger than 30. The first problem we'll consider is the following. Suppose you come to learn that in a study of 80 randomly selected college students, you randomly select 80 college students, the study found a mean of 4.8 years to graduate. That is, on average, it took 4.8 years for a college student for college graduate to have graduated. So let me change that. It's not just any college students, because sometimes they don't graduate. So let's only consider the college grads. Now, assuming that sigma is 2.2 years, construct a 95% confident interval estimate of the population mean. Construct a 95% confident interval estimate of the population mean. Well, remember that the interval, the confident interval, is x minus e, x bar minus e is less than mu, which is less than x bar plus e. This means that the true population mean is in between this value and that value. We all know how to do simple subtraction and simple addition. The only thing is we have to know where we're adding and subtracting. Well, when it comes to x bar, that's not a problem, because they told us, and remember x bar is the sample average, and they told us that that sample average was 4.8. Now we need to find e. We'll add them. We'll get the value over here. We will then subtract those two values, and we'll get the x bar minus e. So we need to find out what e is. And e is nothing more than z sub alpha over 2 times sigma divided by the square root of n. Now, alpha in our case is, since we want a 95% confident interval, alpha is 1 minus that. Remember, 95% is 0.95. And that leaves you with 0.05. Like I said, it might not be a crazy idea to think dollars and cents. You have $1, you take away 95 cents, you have a nickel. And the nickel is $0.05. But there really are no units. Okay, divide by 2, because we want z sub alpha over 2. Divide by 2, and you get 0.025. And when you look that up, 0.025 in the z table, you will learn that z is 1.96. Okay, so z sub alpha over 2 is 1.96 times sigma, which they told us is 2.2 years, 2.2, and now we divide by the square root of n, and n is 80. They did a study of 80 students. Okay, let me just get rid of this because I need the space. And if you crank out this arithmetic, you will get some number, 0.504. This is 0.504. Okay, so now I know E, 0.504. If you like, you can put the 2 zeros in. Well, if I happen to add these two numbers, I would get 5.304. Okay, 5.304. X bar plus E. Now I'm going to subtract them. So you have 4.800 minus 0.504. You really should get 4.296. Do the subtraction and you'll get it. 4.296. And that is your answer. The mean is in between 4.296 and 5.304. Very straightforward, don't panic. If they give you sigma, then you use this formula. You need sigma, x bar, and you have to find the E. Let's do another problem like this. Suppose in a study of 150 randomly selected motorcyclists killed in crashes. Suppose they had a mean age of 37.1 years. So, you find some statistics for people who got killed in motorcycle crashes. And you took the first 150 data from this big list. Or you randomly selected 150 motorcyclists who were killed in car crashes. And you calculated the mean of these 150, and you found it to be 37.1. And assuming sigma is 12 years, we want to construct a 99% confident interval estimate of the mean age for all motorcyclists killed in crashes. So basically, using this study with a sample of 150, you want to make an estimate for the mean age for all motorcyclists who unfortunately get killed in a crash. So now, the thing is, does it satisfy our requirement? The answer is yes, because n is bigger than 30. N, which is 150, is bigger than 30. If this was my class, you'd have to state that. That shows me that you made sure that you can use this test. Now, we know x bar. This was the average age of the sample. That's x bar. So what we need to find is E. But finding E is straightforward. E is V sub alpha over 2 times sigma over the square root of n. Well, alpha is 1 minus. We want a 99% confident interval estimate. So it's 0.99, and 1 minus that is 0.01. And if you happen to divide this by 2, you get 0.005. And that corresponds to 2.575 in the Z table. You look, here's the Z table. Somewhere you're going to see 0.005, and right above it, well, actually, this is a special one. Usually on the bottom of your Z table, it has an asterisk, and it says that for the Z value, that's the area. But basically, the number right before this is going to have 2.5 here and 7 here. That's the number right before 2.7, right before 005. And the number immediately to the right of it is going to have an 8 above it. And it turns out that right smack in the middle of those two numbers is going to be 0.005. That's why they took the average. The average of 2.576. I meant to say 2.57, and 2.58 is 2.575. So when it comes to that special value, 99%, alpha over 2 is going to equal 0.005, and the z-score is 2.575. It's one of those special cases. There's two of those special cases, and they're outlined in the bottom of your z-table. Okay, so this z sub alpha over 2 is 2.575, and then you multiply by sigma, which they said to assume that sigma is 12. So there's no reason why we shouldn't assume that. Divided by the square root of n, where n is 150. If you multiply 2.575 and then multiply that by 12 and then divide by the square root of 150, you will get 2.52. So that's E. E is 2.52. If you add these numbers, you get 39.63. If you add. If you happen to subtract these two numbers, you would get 34.58. And that's your confident interval. That's the smallest number. That's E. That's x bar minus E. X bar minus E is less than mu, which is less than x bar plus E, which is 39.63. X bar plus E is 39.63, and x bar minus E is 34.47. And 99% of the times, the true mean of the entire population will be between 34.58 years and 39.63 years. Okay, 99% of the times, the true average would be somewhere in between there. If you happen to know the true mean of each of the true population of all people killed in motorcycle crashes, and you took a sample of 150, We took many samples of 150. 99% of the times, that true age of the motorcyclist who got killed will be in between, that will be within that confident interval. Okay, now let's try to find N. You have a video company, and they're concerned about losing income due to slugs being used in their video games. If you find a washer that happens to be the same weight, so your machines could detect coins in a couple of ways. It can detect them by size. So if you find any washer, say, that's the same size as a quarter, depending upon the game, that washer might actually activate the game, or whatever machine that takes the quarter. Other machines check the weight. Possibly they don't even check the size. They just check the weight. Now, no two quarters are exactly the same weight. There's always some variation. I mean, it can be a little bit dirty and you want the machine to accept it. So another way is the machine can check the weight of the object, whether it be a coin or a slug or what have you. And if it's within a certain limit, it will accept the coin, and in this case, you can play your video game. If it's outside this weight, you can't play your video game. Well, this company, their machines check the weights of the coin or of their slug. And if it's within, so now what happens is, if you have a machine that checks the weight of the coin and the variation is big, there's a big variation, well, almost, I mean, if it's big enough, any washer would act, when you put it into the machine, will activate the machine. It would recognize it as a quarter. So this company has been losing too much money. So what they decided to do is have some other mechanism that checks the weight more rigorously. It doesn't have such a big variation. Okay, so like I said, they decide to readjust their machine to only accept quarters within a certain weight limit. So the company must estimate the mean weight for the quarters. So they take real quarters and they want to estimate the mean weight. And they want to know is, how many should they weigh? How many should they find the average weight for if they want to be 99% confident that the sample mean is within some amount of their true average weight of all quarters. When we 99% confident that their true weight is within 0.025 grams of the population mean. Actually, that their sample weight is within 0.025 of the population mean. And the formula is straightforward. N is equal to Z sub alpha over 2 times sigma over E. And you need to square this. You need to square that. Well, what is alpha over 2? Well, alpha is 1 minus 0.99, which leaves us with the penny. Divide by 2, divide by 2. Well, now you have half a penny, 0.005. And like before, that corresponds to 2.575. right? So equals Z sub alpha over 2 is 2.575 times sigma. Okay, assume sigma is a good one. How about 0.068 grams? 0.068, and then we divide by E. You want the sample weight to be within this amount. That is, that's your error. That's the hardest part of this problem, in my opinion, to realize that's the error. And then once you calculate that, you have to square it. It does say to square it. And if you do this, you get some more space done, you get a cutoff number. Turns out that this number is 49.056016 to a number of decimal places. If n is this number or more, you can be 99% confident that you will be 0.025 within the true population mean. If you're that number, 49.056016 or more, you can be 99% confident that you're within 0.025 grams the population mean. If you're below this number, you are not 99% confident. But how can a company check 49 and a fraction of quarters? Well, you can't. So you have to bump it up. You go to the next integer. You always round up. You do not round off. You round up. If you rounded this number off to the nearest integer, you'll get 49. But that won't work because the exact cutoff is 49.056016. You have to test that many number of quarters to be 99% confidence to be within your margin of error, 0.025 grams. So the answer to this problem is 50. Round up. If you left the answer like this, you'd lose a point. You round it up. You don't lose the point. If it turned out that n was exactly 52, then don't round it, don't bump it up to 53. 52 would be fine. Okay, let's try one more. Excuse me a moment. Okay. Suppose you want to estimate the mean weight loss of people 1 year after dieting. Okay, a lot of people, they lose weight, but then they put it back on fairly quickly. So, if you wanted to decide which diet is, quote, a good one, it's not the greatest idea to see, how much weight the average person lost right after finishing the diet. Suppose the diet is for 6 weeks. So you check to see the average weight loss of these people after 6 weeks. Now, is that number going to be as good, as meaningful as checking the weight loss of these same people a year after they finished dieting? The better judge of a good diet is how the weight loss of the people after a year. If you put the weight back on, it's not good. Okay, so you want to estimate how many people you should survey. Now, so the question is, how many people should you survey? And you want to be 95% confident that the sample mean is within. The sample mean is within, so here's E, is within a quarter pound, 0.25 pounds, of what? The true population mean. Of the true population mean. That is, what's the true population mean? That's the mean for each and every person who ever dieted. Well, that may not be true. I mean, times change. Now you have to define your population. Your population might be the people who started the diet on January 1st, 2009. Or better yet, so you don't have to wait a year, calendar just changed to 2009, you can survey how many people, that's the question, who started their diet January 1st, 2008. And now that it's already 2009, you could do your statistics and find out if it's a good diet or not. Now, you want to assume the population standard deviation is 0.068 pounds. So when they ask you for how many, you just have to say, oh, that's sigma sub alpha over 2, v sub alpha over 2, times sigma over E quantity squared. They ask you for n, sigma, z, let's start over. They ask you for the sample size. You say, oh, that's z sub alpha over 2 times sigma over n, over E. And we have to find z sub alpha over 2. Well, alpha is 1 minus the confidence level, 0.95, which is 0.05. You divide it by 2 because the formula says divide it by 2. Whatever you do, don't go against the formula. Okay. And for 0.025, when you find that in the interior of the z table, when you find 0.025, it is going to have 1.9 to the left and 0.06 above for a z-score of 1.96. Okay. So now we have the z-score. So let's get rid of this because it's right in my space. So z is 1.96. Sigma is 0.068, and we divide this by E. You want the sample mean to be within 0.25 pounds. That's E, 0.25, a quarter. And whatever the value is within those big brackets, now you go and you square it. It's about 5. Yeah, it's, how about we use for E 0.025. 0.025. The reason I didn't like that using 0.25 because we weren't going to break 30. We're going to get 49.05 and other digits. So you go back and you say n is not 60, excuse me. You go you should use n equals 50. Bump this up. And then you should say, unlike what I didn't do in the last problem, you should say that it's bigger than 30. Okay, when we said that n was 50, we should say that is bigger than 30. Okay, remember, we can't use these techniques of this section if n is not bigger than 30. N must be bigger than 30. And on that note, that finishes this section. Good luck with it.